So today I will prove Hahn-Jordan Theorem. For that we will consider functions, new, which are defined on a sigma algebra and which take value on the extended line. So now I'm not assuming anymore that the function which is defined on the sigma algebra takes non-negative values, but I'm accepting negative and positive values. I will always assume, so remember that we have a set omega and we have a sigma algebra of subsets of omega. I will always assume that nu of the empty set is equal to 0 and that nu is sigma additive. So before I state the Hahn-Jordan theorem, I will prove certain properties of these functions which have already been proved in the case in which nu takes non-negative values, but I will repeat these proofs just to have a self-contained argument. So my first observation, my first lemma is very simple. And before stating this lemma, let me just observe the following. Here I'm assuming that that nu is sigma additive. So there is a consequence of that, is that if I take two sets E and F, which are disjoint, then since nu is sigma additive, it's additive, the measure nu of E union F, it's equal to nu of E plus nu of F. So when I'm saying that nu it's defined on this sigma algebra, it means that it's well defined. And since it's well defined, this means that it's not possible to have two disjoint sets, one of them taking the value plus infinity and the other one taking the value minus infinity, because in that case the measure of E union F would not be defined, right? Because by additivity that would be equal to these two quantities, the sum of these two quantities, and if one of them is plus infinity and the other is minus infinity, this sum doesn't make sense. So it's implicit in these properties that there do not exist two sets E and F whose intersection is empty and whose values are plus and minus infinity. There is also a second consequence of this fact, is that well, since nu is sigma additive, consider a sequence Ej of sets in F which are disjoint 2 by 2. So the intersection of Ej and Ek, it's empty for j different from k. Then by sigma additivity, nu of the sum of Ej, it's equal to the sum of nu of Ej. Right? Well, of course, the value of the left-hand side doesn't change if I change the orders of the sets Ej, if I change the order of the summation. So this means that this value, the value of the right-hand side, does not change if I modify the order of summation. And this means that either this series is absolutely convergent or it is divergent in the sense that if I sum only over the indices j such that nu of Ej it's positive or non-negative, and if I do the same thing but for the indices for which nu of ej is negative, and let's say that I take the minus side to make that positive, well, one of these two sums, it's finite. They can't be both equal to plus infinity, right? Because otherwise that sum would depend on the other, and we know that it doesn't depend on the other because it is equal to the left-hand side. So it's implicit in this, well, when I assume these two conditions, that these two properties hold. Okay, so that there are no two sets with plus and minus infinity values if they are disjoint, and also that, well, whenever we have a sequence of 2 by 2 disjoint sets, the sum of the measures is either absolutely convergent or it's diverging in the sense that one of these two sums it's finite. So I will not repeat that. And now I will extend these properties, some of these properties, in the following lemma. So let me take two sets, E and F. Of course, I always assume that they are in the sigma algebra. I'm not repeating that, but let's assume that E is contained in F. Then what I claim is that, well, either mu of E, it's finite, and in this case, nu of F minus E, it's equal to nu of F minus nu of E, or nu of E, it's equal to plus infinity, say, and if nu of E it's equal to plus infinity and E it's contained in F, then nu of F it's equal to plus infinity. And the same property holds if nu of E is equal to minus infinity. So if nu of E it's equal to minus infinity, nu of F it's also equal to minus infinity. So let me prove these two simple properties. So let's first prove A. So I'm assuming that E of F, E it's contained in F, and that nu of E it's finite. Right? Well, I can always write F as E union F minus E. I can use the additivity of nu to write that nu of F it's equal to nu of E plus nu of F minus E, because these two sets are disjoint. And now, since we are assuming that nu of E is finite, I can subtract nu of E on both sides to get that nu of F minus nu of E it's equal to nu of F minus E, as I claimed. We can also prove B. So B, we're assuming that nu of E is equal to plus infinity. So let's go back to this identity. If nu of E it's equal to plus infinity, well, nu F minus E it's disjoint from E, so it can't take the value minus infinity. So it's either a real number or it's equal to plus infinity. In both cases, nu of E it's equal to plus infinity. So if nu of E it's equal to plus infinity, then we know that nu of F it's also equal to plus infinity. Now, if nu of E it's equal to minus infinity, we can repeat the same argument. These two sets are disjoint, so this set can't take the value plus infinity. So it's either a real number or this measure it's either a real number or it's equal to minus infinity. In both cases, we get that nu of F it's equal to minus infinity, so that if nu of e it's equal to minus infinity, then nu of f it's equal to minus infinity. So if you have any set E whose measure it's either plus infinity or minus infinity, any set F which contains that set has to have the same measure. So this is a first property of these sigma additive functions. So let me prove a second simple property, which I will state as a lemma. Let's assume that we have a set E whose measure it's equal to plus infinity. And let's take another set F. Then I claim that nu of f cannot take the value minus infinity. So we have seen this property if E and F are disjoint. Now I claim that in fact this property holds always, so that you can't have in the sigma algebra F a set E whose value it's equal to plus infinity and a set F whose value it's equal to minus infinity. So this means that if there is one set whose value is plus infinity, then all other sets must take either a real value or a value equal to plus infinity. So let's prove that. So let me draw here the set E and here the set F. And I'm assuming that nu of E it's equal to plus infinity. Okay. So here's the intersection of E and F. It can take it cannot take the value minus infinity, because if it takes the value minus infinity, it's contained in E. That would imply, by the previous lemma, that the measure of E it's equal to minus infinity, and we know that the measure it's equal to plus infinity. So the value of the measure of the intersection of E and F cannot take the value minus infinity. It can take either a real number or the value plus infinity. So if it takes a real number, since the measure of E it's equal to the measure of E minus F plus the measure of the intersection, which by assumption it's equal to C. So let me write that. We know that nu of E it's equal to nu of E intersection F plus nu of E minus F. So if this value it's a real number, which I'm assuming here, since nu of E it's equal to plus infinity, for this identity to hold, we need that the measure of E minus F to be plus infinity. So this means that the measure of E minus F is plus infinity, and therefore the measure of F minus E, which is, or the measure of F which is disjoint from E minus F, cannot be minus infinity. Okay? Because so we know that the measure of E minus F it's plus infinity. Since F it's disjoint for E minus F, we can't have nu of F equal to minus infinity, because we have seen that as a remark before. So this proves that nu of F cannot be equal to minus infinity if the value of the measure of E intersection F it's a real number. So let's consider the last case, the case in which the measure of E intersection F it's equal to plus infinity. So if the measure of the intersection it's equal to plus infinity, since the intersection is contained in F, we have seen that in that case nu of F it's equal to plus infinity. Okay? And therefore we have seen that in all three cases we can't have nu of f equal to minus infinity. Right? So this proves the lemma, and so the lemma says that either this function, so either nu takes value between minus infinity and plus infinity for all f, or nu of f belongs to minus infinity plus infinity for all f. And from now on, without loss of generality, I will assume that the first alternative holds, so that nu of f never takes the value minus infinity. And but this is without generality. We don't lose any generality assuming that as some. So you can just take minus nu to get to go from the second alternative to the first alternative. So let me now state a new lemma, which will be important. By the way, I just realized that here, it's in fact written in this way. I'm sorry. So we will prove that nu, it's continuous from below, and it's continuous. Well, remember that we are assuming that nu it's sigma additive, so I will prove that nu it's continuous from below and from above. And the proof it's exactly the same that I presented in the first lectures, comparing continuity from above and from below with sigma additivity. So let me just remind you that what is continuity from below. This means that if we have a sequence of sets En increasing, so these are sets in the sigma algebra such that En it's included in En plus 1, and the claim is that nu of En converges to nu of the union of En. Just observe that here now the sequence is not increasing anymore because, well, maybe you have a set En and say that the set En plus 1 it's equal to the set En plus a set which is disjoint from En, let's call it A, but the measure of A, it's negative. Okay? It's negative. So of course nu of En plus 1 it's equal to nu of En plus nu of A, but nu of A it's negative, so the measure of En plus 1 it's smaller than the measure of En. So now that nu is taking real values, it's not true anymore that the sequence it's increasing, but what we claim here is that nu of En converge to nu of the union. And so this is the definition of continuity from below. Continuity from above, it's similar. So now we take a sequence En which is decreasing, and we assume that there exists N0 such that nu of En0 it's finite. So remember that nu of N0 it's always bigger than minus infinity because we are assuming that nu does not take the value minus infinity, but it may take the value plus infinity. So I'm restricting here in the definition of continuity from below to sequences for which there exists a certain index N0 for which the measure of En0 is finite. So it's a real number because it doesn't take the value minus infinity, and here I'm assuming that it does not take also the value of plus infinity. And now again, I'm requiring that nu of En, it's converging to nu of the intersection of En. So this is the definition of continuity from above in the case in which nu takes real values. So we will prove that since nu is sigma additivity, that these two property holds by using exactly the argument we used in order to show that a measure taking non-negative values, it's continuous, provided it's sigma additivity. So this is what we'll do now. So let's prove these assertions. Just remind what was the proof. We have a sequence E1, E2, and so on, which is increasing. So the idea was to define a new sequence of the joint set to use the sigma additivity. So here will be the first set, then the annulus will be the second set, and so on. So we'll define a new sequence, F1, which is E1. F2 will be the annulus, which means that this is a set E2 minus E1. And in general, Fk will be the set Ek minus Ek minus 1. So now we have sets Fj, which belong to the sigma algebra, of course, and which are the joint 2 by 2. So we can, by the sigma additivity, you first observe that the union of the sets F coincides with the union of the sets E. So the union of Ek, it's equal to the union of the set Fk. But the sets Fk are disjoint. So I can write this union as a sum. Now I can use the sigma additivity to write that nu of the sum, it's the sum of nu. Well, this sum, it's clearly the limit of k going from 1 up to n of nu Fk. Now I can use the additivity to write this limit as the limit of nu of k going from 1 up to n of Fk. And if you recall the definition, so I'm taking the union of Fk, k from 1 up to n. So you see that I'm taking E1, then E2 minus E1, so the union of the first two, it's exactly E2. Of the first three will be E3. So the union of the first n is just En. So this is the limit of nu of En. And this proves exactly that nu of En, it's converging to nu of the union, which was the assertion. So this proves the first part of the lemma. So now let's prove the second part. So now I have a sequence En, which is decreasing. So here's E1. But then at a certain point I have a set En0 whose measure is finite. So here is En0. And then I continue. En0 plus 1, and so on. So the idea is now to use the first part to transform this decreasing sequence into an increasing sequence. So the idea will be to define this set as the first set, then the union of these two sets as the second set, and so that we get an increasing sequence. So my first set F1 will be E n 0 minus E n 0 plus 1. So this is the annulus that we see here. This will be the first set. So, of course, En 0 plus 1 is this set. This set here, it's En 0 plus 2. So my second set will be F2, will be En 0 minus En 0 plus 2. And in general, Fk will be En 0 minus En 0 plus k. Well, observe the following. En 0 plus k, it's contained, because this sequence is decreasing, it's contained En 0. So we know that nu of En 0 plus k cannot be equal to minus infinity, because nu does not take the value minus infinity. And, well, it cannot take also the value plus infinity, because if it is equal to plus infinity, then since En 0 contains this set, the measure of En 0 would be equal to plus infinity, but by assumption, it's finite. So for any k larger or equal to 1, the value of nu at this set, it's a real number. So we'll be able to subtract these values. So my first claim is that, well, the sequence En 0 plus k is decreasing to the intersection. So En 0 plus k, it's decreasing, and it's decreasing to the intersection of Ej. This means that the sequence Fk, it's increasing, because we are subtracting these sets, it's increasing to the set En 0 minus the intersection of Ej. So by the first part of the lemma, nu of Fk, it's converging to nu of En 0 minus the intersection. But Fk, it's nu of En 0 minus En 0 plus k. And since the measure of En 0 plus k is a real number, this is nu of En 0 minus nu of En 0 plus k. And for the same reasons, well, since the same argument I used to show that the measure of En 0 plus k is a real number can be used to show that the measure of the intersection of Ej it's a real number. So I can write this difference as En 0 minus nu of the intersection of Ej. So what we have is that this difference, it's converging to that difference. Since nu of En 0 it's a real number, I can subtract nu of En 0 in both sides and conclude that nu of En 0 plus k it's converging to nu of the intersection. And well, but this is exactly to say that nu of Ej it's converging to nu of the intersection of Ej, of Ek, which is what we wanted to prove. So this concludes the first assertion of this lemma, and therefore we know that nu it's continuous from below and it's continuous from above at any set. I can now state the Hahn-Jordan Theorem. So I have nu, which is defined on a sigma algebra F, and which is taking values in minus infinity plus infinity. What I claim is that there exists a set P in the sigma algebra F, and I will represent by n, which is the complement of P. And set P for positive, n for negative, have the following property. If I take a set E, which is included in P, then nu of P of E, it's non-negative. And if I take any set F included in N, nu of F, it's non-negative. So P concentrates all the positive part of nu, and N concentrates all the negative parts of nu. So this is called the Hand Decomposition, and I will give you an example to illustrate the fact that these sets P and N are not unique. So just to fix this point, consider that you have in the line, so you are working, say, in the Borel sets of the line, and you take the Lebesgue measure. Now you take a function f, which is defined on R and takes real values. And let's say that it's continuous, so let me take here a function f. So let's say that here's the example of function. It's equal to 0 everywhere, so there is a set A in which is strictly positive and a set B which is strictly negative. And let me define a measure mu associated to f. So this measure mu associated to f, it's just integrate f on the set E with respect to the Lebesgue measure. Right, so you see that if I take P as n, but I can here, let's say, include in P this set. Let me, P will be the set A. So I want to find here a set. So this, observe that this function takes negative and positive values. If E is a subset of A, this integral will be positive. If E is a subset of B, this integral will take negative values. So mu of f takes positive and negative values. And now I want to decompose the line in two sets, a positive part and a negative part, such that each subset of the positive part will have positive measure, and each subset of the negative part will have negative measure. So it's clear that for P I will take at least the set A, and then I can add any subset of these intervals. Okay. So let's say that I have here an interval E1, E2, and E3. I can add to A any subset of E1 union E2 union E3. And of course, if E is a subset of P, then mu f of E will be non-negative, and any subset of, if I define n as the complement of P, any subset f of n will have negative value. So you see, I have freedom in choosing I. So it's clear that in this decomposition, the set P and the set N are not unique. And in this proof, what we want to obtain, we want to find out these two sets, A and B, in which the positive part of the measure is concentrated. So how can we find these sets? This is the proof of the Hahn theorem. So this decomposition in two sets, it's called the Hand Decomposition of a measure. So this is the goal of this lecture. It's proving this statement. And before proving it, let me give you a sketch of the proof. So let me sketch the proof. What I will do is the following. I will define alpha to be the infimum of nu of A, where I'm taking A as all subsets in F. So we know that nu of alpha of A, it's always larger or equal to minus infinity, but it's not clear if alpha can be equal to minus infinity or not, right? Though nu of A, it's always strictly greater than minus infinity, maybe the infimum it's equal to minus infinity. So the first step of the proof will be to show that in fact alpha cannot be equal to minus infinity, and we will prove that by showing that if alpha is equal to minus infinity, then I will construct a set whose measure is minus infinity. So this is the first step. Then once we show that alpha is strictly bigger than minus infinity, the step 2 will be to find a set n, which I will call n, such that nu of n it's exactly equal to alpha, which is the infimum. And now I claim that this set n has exactly all the properties of the theorem. And this is clear because, well, let me represent by P the set n complement. And let's consider set E, which is contained in P. Assume that nu of E it's negative. Well, then if nu of E it's negative, I can just consider the set n union E. By additivity, nu of n of E it's nu of n plus nu of E. Nu of n it's equal to alpha, and nu of E by assumption is strictly negative, so this value is strictly negative, and we have a contradiction with the definition of alpha because we obtain a set which is n union E whose measure is strictly less than alpha, which is a contradiction with the definition of alpha. So this shows that any subset of P has to have measure greater or equal to 0. And the same argument applies to n. So let's take a set F, which is contained in M, and assume that nu of F it's positive, strictly positive. Then, so here's the set N, and here I obtain a set F whose measure is strictly positive. And so what shall I do? Well, that's easy. We will consider the set n minus f. So first observe that nu of f cannot be equal to plus infinity, because if nu of f was equal to plus infinity, since f is contained in n, we would have that nu of n is equal to plus infinity, but by assumption nu of n is equal to alpha, which is not equal to plus infinity, since this infimum is certainly less than or equal to 0 because the empty set has measure 0. So we can't have nu of f equal to plus infinity. It has to be a strictly positive real number. So now let's consider nu of n minus f. Since nu of f it's a real number, this is nu of n minus nu of f. Nu of n is equal to alpha. By assumption, nu of f is strictly positive, so this is strictly smaller than alpha, and it's again a contradiction with the definition of alpha. So, if we are able to show that there exists a set n in f such that nu of n is equal to alpha, then we have our decomposition by setting p as the complement of n. So n will be the negative part of the measure, and p will be the positive, will concentrate the positive part of the measure. So this is the idea of the proof. We'll define alpha. We'll first show that alpha is strictly bigger than minus infinity, and then we'll find the set n such that nu of n is equal to alpha. So let's go to the proof. Draw a picture here. So here's the set omega. Let me define by alpha as the infimum over all sets A in F of nu of A. And my claim is that alpha is strictly bigger than minus infinity. And I will prove that by contradiction. So I'll assume that alpha is equal to minus infinity. And as I said, I will show that there exists in this case a set B whose measure is equal to minus infinity. And for that, I will use an induction argument. So I will construct a sequence of sets A, K, for K larger than 0, which such that AK contains always AK plus 1. And I will also construct a sequence of sets BK for K now larger than 1, and nu of BK will always be larger than minus K. But I will explain during the proof more precisely which sets are these ones. So let's start our construction. I will first declare A0 to be equal to omega. Right? And I will define as lambda of a set C as the infimum of nu of E for all E contained in C. So this means that nu of A0, which is nu of omega, it's equal to alpha, which I'm assuming to be equal to minus infinity. Okay. And so this property will be kept by the sets A. Lambda of A will always be minus infinity. Okay, so now let's start our construction of B. Well, since lambda of A0 it's minus infinity, so this infimum over all subsets of A0 it's minus infinity, that means that I can find at least one whose measure is less or equal than minus 1. So there exists a set which I will call B1, which is contained in A0, and such that nu of B1 it's less or equal than minus 1. Okay. Because, well, the infimum, by definition, lambda of A0, this infimum it's minus infinity, therefore I can find one which has a measure minus 1. So here is my set B1. So this is the set B1. And now I want to define A1. And the property I want is that A1 will be a subset of A0, but the important property which I want to explore is that lambda of A1 is minus infinity. So A1 will be either B1, or let me write that. A1, we will have two choices for A1. It will be either B1 or it will be A0 minus B1. And how should I choose A1? Well, what I claim is that either if B1, lambda of B1 is equal to minus infinity. Assume that lambda of B1 is equal to minus infinity. In this case, I will set A1 to be equal to B1. So if lambda B1, which is defined here, so I define this at B1, I looked at the infimum of all subsets of B1, and I check if this infimum is equal to minus infinity or not. If it's equal to minus infinity, then I define A1 as B1. Well, but it might happen that lambda of B1, it's larger than minus infinity. But in this case, I claim that lambda of A1 minus A0 minus B1 it's equal to minus infinity. Why is that? Well, assume that lambda of B1 it's larger than minus infinity, and lambda of A0, by contradiction, assume that lambda of B0 minus A1 it's minus infinity. So this means that all subsets of B1 have a measure which is larger or equal than lambda of B1, which is strictly larger than minus infinity, and all subsets of A0 minus B1 have a measure which is bounded below by this value, which is a real number. If this is the case, then we can't have the fact that lambda of A0 is minus infinity, right? If I take any set E contained in A0, then the measure of AE it's equal to the measure of E intersection B1 plus the measure of E intersection A0 minus B1, right? Because E is contained in A0, so either either it has intersection with B1 or it has a piece in lambda 0 minus B1. By definition of lambda B1, this set here, it's the measure of this set, it's larger than the infimum, and the infimum I represent by lambda B1. The measure of this set, it's bounded below by the infimum, and the infimum, it's lambda I represented by lambda 0 B1. So any subset E of A0 has measure which is bounded below by this real number, and therefore the infimum it's bounded. So we just proved that lambda of A0 it's larger or equal than this sum, and since this one it's minus infinity, at least one of these two has to be equal to minus infinity. Therefore, if lambda of B1 is strictly bigger than minus infinity, we must have that lambda of A0 B1 is equal to minus infinity. Okay, so this proves that we have this dichotomy. If this one it's not minus infinity, then this one has to be minus infinity. And therefore, what is clear is that lambda of A1 it's always equal to minus infinity, right? Because if lambda of b1 is equal to minus infinity, we set a1 to be b1, and therefore we keep that property. Well, but if not, then lambda of a0 minus b1 is equal to minus infinity, and we set a1 to be a0 minus b1. So in the second case, I will say that we have a bifurcation. So if a1 has been chosen as a0 minus b1, then we say that there is a bifurcation. So a1 will be either b1 or it will be a0 minus b1. In the case in which a1 is equal to a0 minus b1, we say that there is a bifurcation. And this concludes the first step. So we started with a0, we construct b1 and a1. And what are the properties of b1 and a1? Well, a1, it's contained in a0, and lambda of a1, it's equal to minus infinity. And b1, it's also contained in a0. So you see the sequence A of sets A will be decreasing, while the sets B will always be contained in the previous A. Once we conclude the first step, we can repeat the argument, because this argument started from the assumption that lambda of a0 is equal to minus infinity. But this is exactly what happens with a1. Lambda of a1 is equal to minus infinity. So just to try to explain this proof, let's assume that a1 is equal to b1 in the first step. And now we will construct b2. But b2 so we know that lambda of a1 is equal to minus infinity. So we can find a set b2. Since lambda, this infimum, it's minus infinity, we can clearly find one set which is contained in a1 and whose measure is less than or equal to minus 2. So b1 had a measure less than or equal to minus 1. Now we'll find the set b2, which is contained in a1 and whose measure it's now less than minus 2. So in my example, a1 was equal to b1, so we could find the set b2 contained in a1 and whose measure is equal to minus 2. And now again I will claim that either, since lambda of a1 is equal to minus infinity, either lambda of b2 is minus infinity or lambda of a1 minus b2 is equal to minus infinity. So I will define a new set, which is a2, which will be equal to b2 if lambda of b2 is minus infinity, and it will be equal to a1 minus b2 if not. But in that case, we know that lambda of a1 minus b2 it's equal to minus infinity by the argument I just gave. So in any case, lambda of a2 it's equal to minus infinity. And again, if I define a2 as a1 minus b2, I'll say that there is a bifurcation. So let's say that in my example, lambda of b2 was strictly bigger than minus infinity, and therefore we set lambda 2 as equal to lambda 1 minus b2. And what I'm doing here, well, in this example, I'm trying to illustrate that once you have a bifurcation, and so these are generations, say, so this is generation 0, generation 1, generation 2, and say that at generation 2 I had a bifurcation. Well, as you see, A1 it's contained in A0, A2 it's contained in A1, because B2 is contained in A1. So this sequence of sets A's are all, this is a decreasing sequence. So let me write that. So what we are obtaining here, it's a sequence AK which is decreasing. And what's important in my argument now is the fact that, well, B2, it's contained in A1, B1 was contained in A0, so we have also the fact that BK, it's contained in AK minus 1. So maybe I will write that AK also contain BK plus 1. Well, but what does that mean? That means that we had a bifurcation at level 2. So this means that all the next sets A and B will be contained in A2. So the set B3, the set A3 and the set B3, the set A4 and the set B4, they will all be contained in the set A2. Because B3 is contained in A2, B4 is contained in A3, but A3 is contained in A2, and so on. So all the next sets will be contained in A2, and therefore they will be disjoint from B2. So anytime we have a bifurcation, the next generations of sets B will be all disjoint from the set at which a bifurcation occurred. So this means that if now at certain further level I have a bifurcation, so I have here a set BK, but I choose AK as this set, then all the next subsets B will be contained in this set, therefore they will be disjoint from that one and disjoint from that one. So I hope that you accepted this fact that once we have a bifurcation, then all the next sets B will be disjoint from the set just constructed. So let me state that in a formal way, in a rigorous way. So what I claim is that I can construct a sequence of sets AK and BK such that these two properties hold, and such that lambda of AK it's always equal to minus infinity, and mu of BK it's always less or equal than minus K. Okay? So we proved that for K equal to 1 and K equal to 2, but you can just repeat the argument and obtained with that definition, replacing 2 by K, you construct your family of sets BK and AK. Right? So if I just replace 2 by K and 1 by K minus 1, with this argument, you iterate and you construct this sequence of sets AK. So the important facts here are that AK contains AK plus 1 and contains BK plus 1, that mu of BK is less than minus K, and lambda AK it's equal to minus infinity. So let me summarize what we did up to now. We construct so this family of sets AK, which is a decreasing sequence. So AK contains AK plus 1, and lambda of AK, it's always equal to minus infinity. And then we have sequence of sets BK, in which BK is such that nu of BK it's less or equal than minus K, and BK it's also contained in AK plus minus 1. So I'll write that BK plus 1, it's in fact contained in AK. And AK plus 1 can be either equal to BK plus 1, or it can be equal to AK minus BK plus 1. And in that second case, I say that there is a bifurcation. And what I want to make precise is that once I have a bifurcation, then all next sets Bj are disjoint from that set. So assume that there exists a bifurcation at level at a generation. So let's say that it's K. So this means that assume that AK plus 1 it's equal to AK minus BK plus 1. Right, so this means that at certain point I have here a set AK. I have chosen a set BK plus 1, but I decided that my set AK plus 1 will be in fact AK minus BK plus 1. And what I want to show is that if J it's larger than K plus 1, Bj intersection BK plus 1 it's empty. Okay. So I want to show that if I have a bifurcation at generation, what I'm calling generation K plus 1, all the next sets have Bj's have no intersection with Bk plus 1. So this is what I want. So this is a bifurcation, in fact a generation, what I'm calling generation K plus 1. Right? So at generation K plus 1 I decided to choose, instead of Bk plus 1, I defined AK plus 1 as AK minus Bk plus 1. Well, we know that if J it's larger than K plus 1, all sets, or larger or equal than J plus 1, all sets AJ are contained in AK plus 1. Okay. And we know also that the set Bj plus 1 it's contained in AJ, which is contained in AK plus 1. So this means that since AK plus 1, remember AK plus 1 it's AK minus BK plus 1, this means that AK plus 1 intersection BK plus 1 it's empty. But since Bj plus 1, if J is larger than K plus 1, it's contained in AK plus 1, we also have that Bj plus 1 intersection Bk plus 1 has empty intersection, right? Bj plus 1 it's contained in AK plus 1, and AK plus 1 has no intersection with Bk plus 1. So this means that for any, well, J it's larger than K plus 1, so J plus 1 it's larger than K plus 2. So this means that for all I larger than K plus 2, Bi intersection bk plus 1, it's empty. And this is exactly what I was claiming, right? For any j or I larger than k plus 1, which means I larger or equal than k plus 2, bj intersection bk plus 1, it's empty. So this means, let me insist on that, that once I have a bifurcation, all the next sets bj are such that their intersection with the k plus 1, it's empty. Okay. Now I will be able to construct my set B, which has infinite measure. So there are two alternatives. Either, one, there are a finite number of bifurcations. So this means that there exists n0, such that for n larger than n0, there is no bifurcation. Well, if there is no bifurcation, this means that bk plus 1 is equal to ak plus 1. So this means that bn it's equal to an for n large enough, say for n larger than n0. But the sets A are decreasing. So this means that for n larger than n plus 1, Bn it's contained or in Bn minus 1. So this sequence, it's decreasing sequence. So Bn, it's a decreasing sequence because it's equal to An, and An, it's a decreasing sequence. Well, we know also that nu of Bn, it's less or equal than minus n. We know that nu of Bn, it's not equal to minus infinity because nu does not take the value minus infinity. So this means that nu of Bn, it's always a real number. Therefore, we can apply the continuity from above. Let me call B the intersection of Bn's, and by the continuity from above that I proved, nu of B, it's the limit of nu of Bn. Right? Remember that to use the continuity from above, I must be sure that there exists one set n whose measure it's not equal to plus infinity, but in fact this is true for all n. Well, but nu of Bn it's less than or equal to minus n, and therefore this limit has to be minus infinity, which is a contradiction, right? Because we just obtained a set B which has measure minus infinity. So it's not possible to have finite number of bifurcation, because if we have a finite number of bifurcation, by taking B as the intersection of Bn, we proved that the measure of B is equal to minus infinity. So now let's consider the second alternative. That there exists an infinite number of bifurcation. So let's take n0, n1, n2, and so on, the generations at which a bifurcation happened. So these are the generations where a bifurcation happened. Well, by this argument, which I just proved, we know that this sequence B and J, it's a sequence of disjoint sets. So if I take the intersection of B and J and B and K for J different from K, this is empty. So if I define B in this case as the union, which is a disjoint union, by the sigma additivity, nu of B it's equal to the sum of nu of B and J. since the measure of b and j is less than or equal to minus nj, this sum is equal to minus infinity. And again, I obtain the set B such that nu of B, the measure of nu of B is equal to minus infinity, which is a contradiction. And therefore, this proves that alpha cannot be equal to minus infinity, because if it were equal to minus infinity, there would exist a set B whose measure is equal to minus infinity. So this proves, completes the proof of the first step of the theorem. Right, so now let's go to the step 2. So we just proved that alpha, given by this infimum, it's strictly positive. Now, step 2, I want to show that there exists a set n such that nu of n is equal to alpha. Well, since alpha is a real number, we can always find a set Cn which approximates. So there exists a set Cn such that, well, alpha is the infimum, so nu of Cn, it's almost equal to the infimum. It's equal to the infimum plus 1 over, say, 2n. Okay, we can always find this set Cn by definition of the infimum. So now let's take the set Cn union Cn plus 1. So we have a sequence of sets. Consider the set Cn union Cn plus 1. Let's take its measure. I can always, by using the additivity, write this measure as the measure of Cn plus the measure of Cn plus 1 minus the measure of the intersection. Right? Well, the measure of Cn, it's bounded by alpha plus 1 over 2 to the power n. The one of Cn plus 1, it's bounded by alpha plus 1 over 2n plus 1. While the measure of the intersection, well, the measure of the intersection should be larger than the infimum, so the measure of the intersection is certainly larger than alpha, which is the infimum, and with the minus sign we get that it's less than or equal to minus alpha. So one of the alpha cancel, and what we get is that the measure of this set is bounded by alpha plus 1 over 2n plus 1 over 2n plus 1. So if we repeat this argument, what we'll get is that nu of the union from k going from n and Ln plus, say, q of Cn, now this is bounded by alpha plus 1 over 2n plus 1 over 2n plus q. And now I will use the continuity from below by sending q to plus infinity. So this set, it's converging to the set in which I'm taking the union for k larger or equal than n of Cn. So as k converges to plus infinity, this set is increasing to that one. Therefore, by the continuity from below, the measure of this set is converging to that one, and therefore we get that the measure of this set is bounded by this infinite sum, and the infinite sum it's less than 2 divided by 2 to the power n. So we obtained that this set now, this union of sets, it has a measure bounded by that expression, but observe that this set now it's a new set, which I'm calling it D. So here it's K, which is not well written, so let me write it more properly. So here's K, I'm sorry. Okay, I'm taking the union from K from n to n plus K. And so now this set here depends on n. I'm calling it dn. And you observe as n increase, these sets are decreasing. And now I can use, since the measure of dn is bounded by this number, I can use the continuity from above to say that if I take d, which is the intersection of the dn, the sets dn, then by the continuity nu of d, the measure of d, it's equal to the limit of these measures, and the limit of these measures, it's bounded by alpha. But since alpha is the infimum, this set d has measure which is greater or equal than alpha, and therefore nu of d, it's exactly equal to alpha, and d, it's our set n. So we obtain a set n whose measure it's equal to alpha. And this completes the proof of the second step. And as I said, once you prove the step 1 and step 2, I mean, after we obtain the set n, it's easy to conclude the proof, because let's represent P as the complement of n. And now I claim that if a set E it's contained in P, nu of E has to have measure larger or equal than E. And this is clear. I proved it already, but let me prove it again. If nu of E it's negative, then if I take the set F as the set n union E, well, since E it's contained in P and P it's n complement, so the intersection of these two sets is empty. Therefore, nu of F it's equal to nu of n plus nu of E. Nu of n it's alpha. Nu of E it's negative, so this measure this set would have measure strictly less than alpha, and this is impossible because alpha is the infimum. So this proves that any subset of P has measure larger or equal than 0. So let me write that. And now I claim that any set F which is contained in n is such that nu of F it's less or equal than 0. And here again I have a set n here. Here I have a set F. So let's assume that nu of F it's positive. It can't have a measure equal to plus infinity because nu of n it's finite. Then if I take the set n minus F, its measure it's equal to nu of n minus nu of F. Nu of n it's alpha. Nu of F it's strictly positive, so this is strictly less than alpha, and this is a contradiction again. So we proved the Hahn decomposition theorem. And now I can define two measures, nu plus and nu minus. So nu plus of a set E would be just to take nu of E intersection P. Okay, so that you see that nu plus of E it's always larger or equal than 0. Nu of a set F would be to take minus nu of F intersection n. And again, we have that nu minus of F it's also always larger or equal than 0. And I can always write nu as nu plus minus nu minus, because if you take a set A, nu of A, you can always write that as nu of A intersection P plus nu of A intersection n, right? Because P and n form a partition of the set omega. Nu of A intersection P, it's just by definition nu plus of A. And nu A intersection n, it's minus nu minus of A. So we obtained two non-negative measures, nu plus and nu minus, and we just wrote nu as nu plus minus nu minus. So this is the Jordan decomposition, and you can prove, as I said, the Hand decomposition is not unique. I mean, these sets P and N are not unique. But if you impose, furthermore, that the support of these two measures, nu plus and nu minus, are disjoint, you can show that this decomposition is unique. But this is not a relevant point. We will never use that. What we will use later in these lectures are the Hand decompositions in which we can obtain these sets P and N. And this completes the lecture today.